All right. Like I said, good afternoon, y'all. Can everyone hear me? All right. In that case, my thought process is to essentially go about the same method that we did yesterday and solve a Taylor series. So the first one that I want y'all to go with, or want y'all to try to solve, is the following series. I'm going to type this out because my stylus isn't working for me right now, and I'll do that. The series that I want y'all to try to find the Taylor series of is 1 plus x raised to the p power. All you know about p that p is a positive integer. So if y'all were here yesterday, essentially what I'm asking y'all to do is to do essentially the same way that we done our problems yesterday. Find the Taylor series representation for it, and I don't want y'all to find the interval of convergence. I just want y'all to find the radius of convergence. And this one's going to be a little bit longer. So I'll give y'all approximately 10 to 15 minutes to work on it. If y'all have questions, make sure you post them on the chat or unmute your mic. All right. Try to find that Taylor series. And if you have questions, let me know. Luke, I saw your comment. Yeah, assume that is a Maclaurin series that we're finding. And to give you a hint, unique, this is a function, not the Taylor series yet, so that's why it's not centered at -1. Give me a status report on this problem. How much fun are we having here? All right, unique is halfway-ish. All right. Alrighty, in that case, I'll give y'all a few minutes to work on it. So if y'all have questions, post them on the chat or mute your mic and just let me know. Give y'all about around 3 to 5 more minutes to work on it. Again, if y'all have questions, let me know. Oh. See a response. Let me reply to that. Alrighty. So give me a status report. How's everyone doing on the problem? I got some messages from people telling me how they're doing on the problem. How about everyone else? All right, in that case, time to go over the solution. All right, so I'm not gonna lie. To find a Maclaurin series for this guy is going to be very annoying. So our f of x currently is 1 plus x to the p power. And so our main work is we're going to find the coefficients evaluated at 0. And when I find those coefficients, I want to check and see if I can notice a pattern. That's going to be the main gimmick of this problem. But first, let's start taking derivatives. First derivative by chain rule combined with the power rule, you get p times 1 plus x to the p minus 1 power. The second derivative of x, p is a constant, so that should stay as there. Now my new exponent is p minus 1 from the first derivative, so I'm going to have p times p minus 1 times 1 plus x raised to p minus 1 by power rule, so p minus 2. Third derivative of x, again by power rule, I have with chain rule p minus 1, p minus 2 times 1 plus x raised to p minus 2 minus 1 by the power rule, so p minus 3, and so on. And before we go and plug in 0, let's go ahead and figure out what the pattern is for the k derivative of that function in general. So where k is referring to just the k derivative that I'm taking. So to give you context, I want to refer to just f of x as k equals 0, meaning I took no derivative. And the pattern that I'm going to try to find is that is what is occurring with the coefficients that are up in front of the 1 plus x. I'm not super worried about the exponents because when I plug in 0, I'll just get 1 raised by an exponent, which will give me 1. So I particularly want to look at the pattern that's going on with the exponents. With the coefficients up front. So I'll rewrite f of x because I'm not actually looking at anything. But now let's look at the first derivative. So what I'm going to try to do is I'm going to try to get that index k to pop in somewhere within that coefficient p. And the way that I see that is for that p, if I want 1 to appear, well, I'm going to add 0, which means I have a -1 plus 1 popping in. And let's write that in blue to make it clear what I'm emphasizing. 1 plus x to the p minus 1. So right now I have, in this case, k equals 1 popping in. Now let's check and see if I could have that pattern repeat. In this case, I'm not going to look at p. I'm now going to look at p minus 1, and I'm going to ask myself, how can I rewrite -1 such that k pops up again? In this case, k will equal 2. And the way to get a -1 with k equals 2 to pop in is to rewrite -1 as -2 plus 1 times the 1 plus x to the p minus 2. So right now I have the k for equals 1 and k equals 2 appearing where that minus sign is going. So let's see if we can follow that pattern again with the third derivative coefficient to check and see if there's a pattern. So p minus 1, and now I have p minus 2, and based on what I'm seeing in the blue, I want to have minus whatever the number k is, or the number of derivatives I'm taking, plus 1. And I can rewrite p minus 2 as p minus 3 plus 1. So I'm still corresponding with the pattern that I'm going by. And the reason why I want to observe that is my observation is telling me that for the kth derivative, the coefficient up front will be p times p minus 1 times p minus 2 times ... until I get to p minus k plus 1, and then times 1 plus x raised to p minus k, which I'll put in pink again. So there's the pattern that we're seeing right now. So for the kth derivative of this function, the coefficients are going to be a lot of products, where the very last coefficient up front will be p minus whatever number of derivatives I'm taking plus 1. Since this is a Maclaurin series, we're going to plug it in at 0. which means our coefficients in our Maclaurin series will be plug in 0 to the function, I'll get 1. Plug in 0 to the first derivative, I'll get p. And based on the pattern we see, I'm just going to get left behind all those coefficients that I currently have. So for the kth derivative at 0, I'm going to have that product of p times p minus 1 times p minus 2 dot 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 keep on going until I get the p minus k plus 1 term. And those are going to be my coefficients when I write down the Maclaurin series for that guy. So now we have that bad boy. Let's go ahead and write out the Maclaurin series. The Maclaurin series is the following. So first we have f of 0 plus the first derivative of the function at the center over 1 factorial. And because it is a Maclaurin series, it'll be x minus 0 plus the second derivative at 0 divided by 2 factorial x minus 0 squared plus dot dot dot. And for x, I'm going to go ahead and write down f to the kth derivative at 0 over k factorial x minus 0 to the kth power. And then because this keeps on going, I'll just put some dots there to note that this just keep on going forever. And now plugging in all those coefficients of purple, I get for f0, 1. For f prime at 0, we got that to be p. So I have p times x plus second derivative evaluated at 0. Well, based on our pattern, that's just going to be p minus 1 plus 1 divided by 2 factorial, or p times p minus 1. So p minus 1 plus 1 over 2 factorial at squared dot dot dot. And note that our kth derivative we're going to have in the numerator p times p minus 1 times p minus 2 dot 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 p minus k plus 1 over k factorial times x to the k, and it's just going to keep on going forever and ever. Thus, the kth derivative or the Taylor series for that guy is going to be super nasty. It's going to be the sum from k goes to 0 to infinity of p times p minus 1, all that product up to p minus k plus 1 divided by k factorial times x to the kth power. And that, my friends, is a very nasty Maclaurin series. Because this is a very special Maclaurin series, it actually has a name. It is called a binomial series. The reason why it's called a binomial series is because this tells us how I can span any binomial 1 plus x raised to the pth power in a general formula. So one example, if I want to expand the cubic root, one thing that y'all learned way back in the day was you just have to do FOIL and then multiply that binomial that you get, or that quadratic, with that binomial, and then you got it. But now use formula, I could just quickly tell you that is the sum going from k to infinity of 3 times 2 times 1 to the p of power. And by using that formula, I could quickly tell you that is just s cubed plus 3x squared plus 3x plus 1. And all I did to get that very quickly was I just used this formula and just kept iterating it until I got to the very end of whatever power I have. Cool fact. So one remark that I do want to make is on the coefficient in that series. Because when you take a couple more math courses for your undergrad career, I'm going to say that you're going to see the binomial series again, but the coefficients are not going to be in that form. So let's go ahead and rewrite that into the form that you're probably going to see that in. So p times p minus 1. First, let's copy it down. P minus k plus 1 over k factorial. And so here's how that coefficient is going to be given to y'all when you take more math courses. I'm going to multiply this whole nasty expression by 1, but the one that I'm choosing is going to be very particular. I'm going to choose p minus k factorial to multiply the numerator and denominator with. And we'll see why very quickly. So p times p minus 1 dot 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 times p minus k plus 1 times the p minus k factorial over k factorial and it times a p minus k factorial. And from yet, I'm only going to do one rewriting for this guy. So right now I have p minus k factorial in the numerator. If I want to expand it, that'll be p minus k times p minus k minus 1 times p minus k minus 2, all until I get 1. If I include everything that was in purple in the numerator, I can rewrite the entire numerator as p factorial, meaning that I can rewrite that coefficient as the form that you're going to see for y'all. So p factorial, k factorial, p minus k factorial. And because of that, mathematicians got cool and they decided, oh, well, let's give this guy a very special name. And they called it the binomial coefficient. Oh, hold on. Do I keep cutting? Is there issues on y'all end of hearing me? I just saw Unique's comment. Okay. 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 In that case, it might be my internet. I don't know. I'll try to see what I can do on my end to fix it. If it's working for now, I'll keep going at it. But hopefully by tomorrow or the end of this week. Crap. Okay. All right. Also, it might be because I'm using my tablet and not my PC. I'm guessing my voice just decided to spike based off of James and Isaac. Yeah. Okay. All right. Let's do that then. How about now? Well, I sadly apologize for doing that for all of y'all. Isaac, as always, your comments are greatly appreciated. If my audio just spiked immediately, I think I might know the issue, but I'll at the end of this meeting, I'll double check my audio on my end to make sure that y'all can hear me without any drop the bass or anything like that, or any cutting. I thank y'all for letting me know about that, because otherwise I would just keep on talking without not realizing it. I'm glad someone enjoys it, Anthony. Glad you have opinions. Oh. All right. Well, let's get back on topic. So mathematicians thought this was a cool thing, so they called it the binomial coefficient. And so if you take, like, for example, Math 302, the way you're going to see this pop up again is if you've taken like any stat course before, a combination, where the way I would think about that is out of P objects, choose K of them. So like I said, pretty neat fact. Now, here is one thing I do want to make a note of, and that's the radius of convergence. The radius of convergence is technically 1 in this scenario. But for the interval of convergence, I may or may not include the endpoints, so I'll make that as a note. But for the interval of convergence, the main thing that's going to factor whether or not I include the endpoints is what P is. So for example, if I did back in that example cubed and plugged in P equals 3, it may or may not give me a I may or may not keep the endpoints, or maybe I do. But because it is very dependent on whatever value that P is, the interval convergence, it'll still be -1 to 1, but whether or not I keep the endpoints will be very dependent on whatever number P I choose. All right. So there's our warm-up example. Any questions on that? Or am I cutting out again? Oh, all right. In that case, I'll give y'all a minute. Take a sip of my water while y'all write that down. Let's not try that. So for yes problem, Anthony, the radius of convergence will be 1. And that's mainly, and the idea behind why people got that was is very similar to a geometric series. So the radius of convergence for this problem is still 1. It's just that the interval of convergence could change based on what value for p I choose. Oh. Detentions taking place in Principal Skinner's office. If y'all caught that reference, that's wonderful. I don't expect y'all to, but if y'all caught that, then it makes me happy a little bit. All right, with that, let's go on with another example of how we could tackle these guys. Oh, that's a good one. So the next problem that I want y'all to do is we talked about the Maclaurin series for just e to the x. But let's go forward a little bit and let's find the Maclaurin series for an arbitrary exponential function. Where b is greater than 0. And to make this more interesting, let's make sure b is not equal to 1. Because then I'll just have 1 and it won't be interesting anymore. So find the Maclaurin series for that guy. And also state the radius of convergence and the interval of convergence. And I'll give y'all about 5 to 10 minutes based on how progress is going. And let me know how y'all are doing. Like I said, if you have a question, post it on the chat. Or if you can unmute your mic and we'll have a chat. curiosity. All right, how's that problem going on y'all's end? Go ahead and give me a status report. Oh, I see some messages. Let me respond to them. All right, give me a status report. How are y'all doing on this problem? All right, give me a status report. How are y'all doing on this problem? And message from a few of you, but not all of you. Comment. Halfway-ish again. All right. I'll give you all a few more minutes then to work on it. Saw a comment pop up, so I'll respond to that. All right. So a couple y'all private message me with the correct answer. But kind of want to get a status report from y'all. How was it finding the Maclaurin series for that guy? You can be pretty honest. Did it suck? Was it perfectly fine? Or what? All right. Update from Unique. How about everyone else? Thank you for being honest, Unique. That's the goal for these Zoom meetings is for us to do problems together and get immediate feedback. Kind of figure out how to solve them. All right, so I'll go ahead and let y'all know that there are two ways to tackle this problem. And I'll do both of them going over the solution. One of the two methods that I'm going to do is kind of our old faithful method in which we take a lot of derivatives, we evaluate at the center, and then write out the Maclaurin series. And then the second one is going a little bit more subtle that I'll be doing. So let's do the first method, or the first way to solve it, which from now on, when we're taking a bunch of derivatives to find the Taylor series, center out a point, I'm going to call it Old Faithful, because while it's tedious work and takes a while, I know that yes, it's going to work. So I'll call it Old Faithful method. All right, let's take a bunch of derivatives. So first, f of x equals b to the x power. A quick review from Math 1060. What's the derivative for a general exponential function? Bingo. There we go. Essentially, copy down the function itself, multiply it by natural log of the base. All right, and we want to take the second derivative. Now note, I'm taking derivative with respect to x, not with b. So that natural log of b is a constant when I take the derivative, which means when I take the derivative of b to the x again, which is b to the x times natural log of b, but I keep in mind that I still have another natural log of b multiplying in there. And I have two numbers being multiplied with the same baits, so I can rewrite that as, there we go, b to the x power times natural log of b squared. And if I take the third derivative, the natural log of b squared is still going to be treated as a constant because I'm taking derivative with respect to x. So that means the third derivative of x will be Again, take derivative of b to the s power again. But note that I still have natural log to the b power squared multiplying in there. Two numbers being multiplied, both of those numbers have the same base. So I can rewrite that as b to the s power times natural log of b cubed. So now we see a pattern going on where for the kth derivative of this function, we want to have b to the s popping in again. Natural log to the b power raised to the kth power, because I'm multiplying natural log of b k times. And then for our Maclaurin series, we're going to plug in the center, which is 0. Anything raised to the 0 power is 1. First derivative at 0 is b to the 0 power times natural log of b. So I'm just left with natural log of b. And if I keep on going, second derivative, I'm just going to have natural log of b squared, which means for the kth derivative of f evaluated at 0, I'm going to have natural log of b raised to the kth power, meaning that the Maclaurin series is going to be f of 0, which we have to equal 1. So 1 plus my first derivative at 0, which we have to be natural log of b, over 1 factorial x times the center, but since the center is 0, it's just going to be x, plus the second derivative evaluated at 0, so natural log of b squared, over 2 factorial times x minus the center squared. And I keep on going to follow that pattern for the kth term, b to the kth power over k factorial x to the kth. And I'll put some dots here to note that I'm adding forever. Which means my Maclaurin series in sum formation is going to be the sum from k equals 0 to infinity, natural log of b to the kth power times x to the kth power divided by k factorial. So there's our lovely Maclaurin series that we're going to be working with. So we have our Maclaurin series. Let's now find the radius of convergence. Because I see the k factorial, I'm going to do the ratio test on that guy to see what's going on. So I'm going to list out a of k and a of k plus 1. So natural log of b raised to the kth power x to the kth power over k factorial. And an a of k plus 1. I'm just replacing k. That's not a k, that's a b. With k plus 1. And I think by now we're pretty good experts on the drill of using ratio test. So I'm going to have L equal to the limit as k goes to infinity of absolute value a of k plus 1 over a of k, which equals the limit as k goes to infinity of the k plus 1 term, so natural log of b, k plus 1 power, s to the k plus 1 power over k plus 1 factorial times the reciprocal of a of k, which will be natural log of b raised to the kth power times x to the kth power. A lot of things get to die off. That k factorial dies, and I'm just left with a k plus 1 in the denominator. That x to the k, that dies off, and I'm just left with an x. The natural log of b to the k dies off, and in the numerator, I'm just left with natural log of b. Let's clean it up a little bit. I have limit as k goes to infinity of natural log of b times x times 1 over k plus 1. And remember, I'm taking limit with respect to k, so anything without a k gets to be treated as a constant. But since I'm inside an absolute value, I'm going to do absolute value of natural log of b times x times the limit as k goes to infinity of absolute value of 1 over k plus 1, but because 1 over k plus 1 is always positive, the absolute value becomes redundant. Because I have the denominator getting super big, but nothing in the numerator, that whole thing is going to go to 0, which means that the L is going to equal 0, which means I'm always less than 1. Which means from our previous Zoom meetings before, the way we interpret that is regardless of what value for x I plug in, I will always have a convergent series, meaning my radius of convergence is infinity, and then my interval of convergence is just going to be any real number that I could think of. So there's the first method of how we could tackle that problem. Now we're going to show the second method of how we could tackle that problem. In this property, I'll put down when you mean for yes one infinite, you're talking about method 2 what I'm using? Is that what you're referring to when you say what's the name for yes one? Okay. I can't think of anything clever, so I'm just going to say I'm going to use properties of power series to get the same answer. All right. And the property that I'm going to use, yeah, Old Faithful after beta testing. All right. So the property that I'm going to use, it's all listed down in purple. And that is if I have a function h of x, which is of the form b times x to the n power, or that exponent is greater or equal to 0. And I already know that f of x has a power series representation. Oh, that's all right, my tablet decided to go up, or I just decided to touch something weird. There we go. Now we're back to crisis averted. All right. Then what that says is I can find a power series representation of a composition of f and h of x by wherever I saw an x originally for the power series representation of f of x, I replace it with h of s. So that's the property of power series I'm going to be using. Let's figure out how we can use it for this problem. So right now, b to the s, that's not, the outside function is not a Maclaurin series or Taylor series or Maclaurin series that I recognize. So let's rewrite it into a form that I recognize. Keep in mind that because this is essentially an exponential function, or a general exponential function, that thing is always positive. Because it is always positive, it makes this operation I'm about to do valid. The e to the natural exponential function and the natural log function are inverses of each other. And because they're inverses of each other, then if I do a composition of a function with its inverse, I am just left with the innermost component after the function and its inverse cancel each other out. And that's why I made the statement that b to the s, a general exponential function, is always positive, because the domain, the domain for a natural log is all positive numbers. So for natural log of b to the x to be a valid operation, I need to guarantee myself that b to the x power was always positive. Well, now since I'm inside a natural log, I'm going to use my property of natural that says exponents inside the natural log become coefficients outside of the natural log. Meaning I can rewrite this as e raised to x times natural log of b. And in the case of the property that I just mentioned, this becomes my h of s, where in this case the coefficient is natural log of b and m is 1. But now that I recognize that, I know the Maclaurin series of e to the x, that's just sum from k equals 0 to infinity of s to the k factorial over k, s to the k over k factorial. So I already know that from previous conversations we've had. Meaning, using the property above, I can rewrite this as the Maclaurin series for e to the x, but instead of wherever I had an x, I replace it with natural log of b of x. And because I'm multiplying two things raised by the same power, that's the exact same thing as me saying sum from k equals 0 to infinity, natural log of b to the kth power over k factorial times x to the kth power, which matches with the answer that we got in the first method of us tackling the problem. Oh, so that gives me a good idea for a YouTube video, because since I have a YouTube channel, I gotta get myself to the point where I can monetize my videos. That'll be a good title for my for one of those videos. But yeah, so this is so method 2 is corresponding to what I talked about. Oh, need lots of red arrows and circles as well to be like Yeah, in the thumbnail, just look at that. No, nothing related to the video, but yeah. Oh, yeah. The arrows will be pointing towards my face with the circle at my mouth. Yeah, that'll be wonderful. All right. But this is kind of corresponding with something that I mentioned yesterday, that while method one is our old faithful, in which I know for a fact this will work to help me find a Taylor series expansion, I'm going to keep in mind that Taylor series or power series, where the coefficients come from a Taylor polynomial. So all the properties that I have for a Taylor series, for a power series, they're fair game for any Taylor series or Maclaurin series that we talk about. Which is why method two is us abusing that fact that a Taylor series is just a very special power series. And we use that to our advantage to tackle that guy. Any questions about how I tackled this problem in the two ways that I did? Let's put it back on. All right. Any questions in general about that problem or any of the other stuff that we did today before I give y'all another example to try? First, I'll take a sip of water. Since sheer amount of awesomeness with method two made me thirsty, but let's go ahead and try to do one final example before our Zoom meeting is over. Here's my idea. Again, and with this example, I want y'all to remember what I said before, that all Taylor series are power series where the coefficients come from Taylor polynomials, because that's going to help y'all out with the next problem. I want in series representation of x squared times cosine of x squared. And so that's going to be my question for y'all. Is find a power series representation for that guy. I'll give y'all about 5 minutes to work on that. If y'all have questions, let me know. See a message. So I'm going to let y'all know. I do not recommend doing the Old Faithful method. The goal of this problem is it possible to use properties of power series and Maclaurin series that I already know to rewrite x squared times cosine of x squared. So the goal of that problem is use whatever tools you can to find a power series representation for x squared. Go in there. So here's kind of my hint, Anthony. Out of these functions, any of these functions that I see, do I already know a Taylor series for one of them? And if so, which Taylor series do I already know? All right, which one? Not quite, Anthony. Not the Taylor series for x squared. But Isaac already let y'all know, and I just saw Luke's comment, which is used in Maclaurin series again. So I already know the Maclaurin series for cosine of x. As that expression. So with that fact now, how can I find a power series representation for that guy? And I'll give y'all a few more minutes to work on it. And go through it. Luke, I just saw your comment. Not quite. because there's only going to be one series that I mainly get to play with. I'm not going to have two series to work with. And I saw a comment. Let me respond to that. All right. So I just saw my on my end is 457. So for the sake of time, quickly go over the solution. So the way I'm going to find this power series representation is I'm going to use the same property that I had that I used when I resolved the last example. And yep, Isaac, you're right. And here's the other property of power series that I'm going to use. So if I have x raised by some power outside of a power series, then I can move that inside my series and rewrite the exponent inside my power series as k plus m. So let's do that now. So x cosine of x squared. So as noted, I know the Maclaurin series for cosine of x. But to use the property that we talked about before, I need a composition inside. And my composition is that x squared. And so what the property is for the last example. Oh, thank you, Luke. I can't read. There should be a square there. Appreciate it. That's equal to x squared times the Maclaurin series of cosine, but instead of x to the 2k power, it's going to be x squared to the 2k power over 2k factorial. X is being raised by a power, being raised by another power, so I get to multiply those two exponents together to give me x squared times the series, and k equals 0 to infinity of -1 to the kth power x to the 4k power divided by 2k factorial. And now I get to use the property above where that x squared outside of the series gets to go back into series, and I can add the exponents as I would expect to give me a final answer of the sum starting off at 0 going off to infinity of -1 to the kth power x raised by the 4k plus 2 power divided by 2k factorial. And that gives me my power series representation for that guy. And that's one thing I want to emphasize with this is that remember our basic Maclaurin series to Taylor series? But from our basic Maclaurin and Taylor series, we can find brand new series from our properties of power series from before, which is the goal of that problem. Any questions on data sample? Any last minute comments? All right. If no last minute comments or questions, I'm going to go ahead and end this Zoom meeting. Tomorrow we're going to have more fun with Taylor series. Oh, what's up, Isaac? See you, Anthony. I'm guessing you're ready down, Isaac?
Okay, can you hear me? I just switched my microphone.
Okay.
All right, so I had a really quick question. So for this problem specifically,
Mhm.
what if that became a 2x cosine of x squared? How would that affect the distribution?
So you're saying if I change that to 2 times x?
Yes.
Not much. So what that will change is that 2 is just a normal coefficient that is there regardless. So I would use the above property with just x, move that x inside, and that would give me 2 times the series sum k equals 0 to infinity of -1 to the kth power x, but instead of at 4k plus 2, it'll be 4k plus 1.
Okay. I see. So we can keep constants out, and the power still applies. Okay, that answers my question. So
Yeah.
2x squared cubed 4, that makes sense.
Yep.
Okay,
If you want, you could move that 2 inside, but since 2 doesn't have the index k, it's your choice.
Okay, yeah, that would just kind of make it bloated. All right, that answers my question. I saw something in MyLab Math on Monday about it, and that answers my question, though. All right, sweet, thank you.
You're welcome.
Sure.
All right, you too. All right, see y'all.